Let's connect two things that sound like they're from completely different worlds. The high-stakes precision of a hospital lab and the huge, global challenge of building a cleaner planet. You're going to see how they're linked by one single, incredibly powerful idea.
So, it all starts with this question. What on earth could possibly connect a glucose test for diabetes with the massive effort to clean up industrial waste? Well, believe it or not, the answer is hiding in plain sight. It's inside every single chemical reaction happening all around us. To get to the bottom of this, our first stop has to be the clinical lab. This is a place where the stakes are incredibly high and where a single number can change everything.
So I want you to picture a lab technician. We'll call him John. He's analyzing a patient's blood sample. And right now, that patient's entire diagnosis, their health, their treatment plan, it all comes down to John's ability to get one number perfect, the amount of glucose in their blood. If it's too high or too low, that's a sign of a really big problem.
Okay, so how in the world does John count something as ridiculously small as a glucose molecule? Well, he uses this amazing concept called the mole. And no, not the furry animal. In chemistry, a mole is just a way of counting. Think of it like a dozen. You know a dozen means 12, while a mole is just the chemist's version of a dozen, but for counting a mind-boggling number of atoms. It's the tool that lets John make sense of a world he can't even see.
And what a number it is. Look at that. That's 602 sextillion, 200 quintillion. It's just an absurdly big number, and it has to be because atoms are so incredibly tiny. This number has a special name, Avogadro's number, and it's basically the magic bridge that lets a chemist like John take something they can weigh, like a blood sample, and know exactly how many molecules are inside.
All right, so the mole lets us count. That's awesome, but the real magic, the real power, comes when we use that count to figure out how things actually combine. So let's get into the basic rules of a chemical reaction.
Way back when, early chemists started noticing this really weird, cool pattern. Elements didn't just mush together randomly. Nope, they combined in these perfect, clean ratios. Like you always needed 2 parts hydrogen for 1 part oxygen to make water. This wasn't a coincidence. It was a huge clue that matter wasn't some continuous goo, but that it was made of these tiny individual building blocks we now call atoms.
And this brings us to a word that sounds way more complicated than it is, stoichiometry. Seriously, don't let the name scare you. All it means is the recipe for a chemical reaction. It tells you exactly how much of your ingredients, your reactants, you need to make a specific amount of your final dish, your product. And the mole? That's the cup or teaspoon you use to measure everything in that recipe.
So here's a quick look at how it works in the real world. First, you write out and balance your chemical equation, your recipe. Then you take the weight of your starting ingredient and you convert it into moles. Now, here's the key. That balanced equation gives you the mole ratio, the secret sauce that tells you exactly how the ingredients combine. You use that ratio to figure out how many moles of your final product you're going to make, and then you just convert that number back into grams. It's this incredibly precise math that runs the entire chemical world.
Now, this kind of precision lets chemists get what's called a high yield. Basically, they get really good at making a lot of the thing they want to make. And for a very long time, that was the only goal. But here's the twist. Just because a process is good at making one thing doesn't actually mean it's good.
So you really have to ask yourself this question. If you make 100 pounds of your product, but you also create 1,000 pounds of toxic waste doing it, was that actually a successful reaction? This question really starts to pick apart what we even mean by efficient.
You see, for decades, the only thing anyone cared about was percent yield. All it asks is, how much of the stuff I wanted did I end up with? But look what it completely ignores. It doesn't care about the leftover ingredients, the nasty byproducts, the energy you burn through. It's like judging a chef only by how good the food tastes without ever looking at the giant mountain of wasted food in the kitchen trash can. And the original process for making ibuprofen is the perfect poster child for this problem. It was a really complex 6-step process that was, yes, very good at making ibuprofen. The big issue? It was even better at making waste. Huge, huge amounts of it.
So this realization, this aha moment that we were totally focused on the wrong metric, it sparked a revolution in the field, a whole new way of thinking called green chemistry.
And this led to a much smarter metric called atom economy. It asks a way better question. Of all the atoms I started with, what percentage of them actually made it into the final product I wanted? It's a measure of elegance, of efficiency, not just brute force output.
And then there's the flip side of that coin, the environmental factor, or E factor. And this one is brutally simple. It just measures the total weight of waste you created for every 1 kilogram of product. With the E factor, there's absolutely nowhere to hide your mess. The goal? Get that number as close to zero as you possibly can. And wow, when you start applying this metric across different industries, the results are kind of staggering. Just look at this chart. Oil refining? Pretty efficient, actually. But as you move into fine chemicals and then pharmaceuticals, the waste just explodes. We're talking about processes that can generate over 100 kilograms of waste for every single kilogram of medicine. 100 to 1? It's wild.
So this is it. This is the moment where our two seemingly separate stories finally crash into each other. The same exact principle of counting atoms that keeps a patient safe in a hospital can be used to protect the entire planet.
So let's go back to ibuprofen. Armed with these new green chemistry ideas, scientists went back to the drawing board. Remember that old Brown process? It had an atom economy of just 40%. The new green process? It's down to just 3 simple steps, and it has an atom economy of 77%. It nearly doubled the efficiency and just slashed the amount of waste.
And you know, this way of thinking, it goes way beyond just a single reaction in a lab. It forces us to zoom out and look at the entire life cycle of everything we make, from how we get the raw materials in the first place, all the way to what happens to the product when we're done with it. The goal is to design waste out of the system from the very, very beginning.
So, we have finally come full circle. The mole, that simple idea for counting tiny particles, is the hero of both stories. It's what John in the lab uses to make sure a patient is safe, and it's what industrial chemists are now using to completely reinvent manufacturing, making sure the atoms we use end up as useful products, not as pollution.
And that leaves us with one last thought to chew on. We have the science. We literally have the ability to count every single atom we use. So the only real question left is, what's stopping us from making every single one of those atoms count?